maybe wait for 2 more minutes, people start to join. Yeah. Right now it's 8:30. Let's get started. First of all, welcome everybody for spending your evening with us to participate in our event. And if you have a question, please post your question on the chat or raise your hand. And let's get started. Let me do the recording first. Call to the cloud. Let's get started.
Okay. Good evening, everyone, or wherever you are, depends on where you are. Good day. So my name is Shanti Deemyad. I am going to talk about some studies that we do on quantum materials and some of the quantum effects in the materials that we do in our lab. So let me tell you a little bit about myself. This is my short bio. I did my undergraduate studies in Sharif University of Technology in physics. I graduated in 1998. Sharif is in Tehran and in Iran, and then I came to Washington University in St. Louis, where I received my PhD in 2004. During my PhD, I studied the superconducting properties of materials at extreme conditions. Specifically, I studied the superconducting properties of lithium, which I'm working in that area, so I'm going to tell you a little bit about that today. After receiving my PhD, I went to Harvard University, and where I was a postdoctoral fellow, and I studied the melting behavior of hydrogen. Hydrogen is the most abundant element in the universe, and it is also extremely important to our understanding of the stars, planets, and the universe around us, and also the basic physics. I found the first evidence of the maximum in the melting line of hydrogen during these studies. And after that, I came to University of Utah, which is in Salt Lake City. Salt Lake City, Utah is on the northeast of California. I think that's the closest, that's the most known state in the United States. And here I'm a head of a high pressure research lab, and I'm a physics professor. This is an image of some of the outdoors of the Salt Lake City and the look of the city overall. These are the pictures of my recent group members, and they're the ones who are behind all the work that is done in the laboratory. They're the ones who collect data. We are experimentalists. Okay, actually, let me stop sharing and restart this. It seems like, yeah. Yes. Sorry, I'm gonna, yes. So they're doing basically all the experiments. So I listened to many of these previous talks in this series, and I was trying to connect my research and see that how this has to do with the main topic of this quantum computing group. And here is how we think about it. Our technology depends on the materials and material properties. And from the Stone Age and Bronze Age and Iron Age to the time that we have may use the very light materials to create, like, for example, aircraft, to semiconductor age and the magnetism for storage of the memory, and also the superconductors that they are very they're not used that often. They're like used they're not used as much as they should in our daily life. We are surrounded by the material properties, and it's extremely important that we find materials that they allow us to do new things. And quantum computing is reliant on the material properties that they obey the quantum mechanical laws and the quantumness and discrete states that the quantum mechanics gives us. And these materials are discovered in the laboratory. And our understanding of how they work allows us to discover new states of matter and find new candidates that they might be good candidates for showing the for quantum computing. So one of the things that is important to think about is that what drives the phase transitions? It's not, we have the periodic table that is a bunch of elements, but materials obviously are forming from combination, many different combinations of the elements in the periodic table. And also they are forming each element, even its purest form, they can take many different phases. So we can use in laboratory, we use temperature, pressure, chemical composition, magnetic field or electric field to push, and also the optics, I mean, the electromagnetic field, in fact, to push materials to new states of matter. And we use them to basically to find and discover new materials, because our ambient pressure experience, ambient condition experience is extremely limited, and the number of materials that they can function that we deal with in our daily life can be very limited. We can do a lot more by expanding our phases space. So, and if you have any questions, please stop me. I would be happy to address any questions. So in my lab, we are particularly interested in the pressure effects. This is something that maybe not many groups they actually use, or it's not, people are not knowing much about the pressure effects. Pressure effects, they have profound effect on the material properties. For example, let's think of like the pencil lid. It's graphite. We know that it is a it's not transparent. We know that it's a material that is two-dimensional. It easily comes off layers. That's what we can write with a pencil. And then you can pressurize this graphite and also add some heat, and it transforms to diamond, which has completely different properties. Both of these are made out of carbon, and however, diamond is, we know that it is transparent to majority of the electromagnetic spectrum. It's a super hard material in 3D. And so it's very different in terms of the graphite. And both of them are precious states of matter, but they're very different. And one is created only under pressure or outside of the ambient condition. You can also actually create diamond with a low pressure, but not at ambient pressure. So this is an example, and many of these materials remain metastable, meaning that you release the pressure, they stay like that, and diamond again is another good example of this. Pressure effects in condensed matter are profound. You can look at this, for example, this is just a phase diagram that I picked up from one of the online sources, and which shows that the typical phase diagram of a material under pressure or changing the chemical composition. And you can see that you are seeing all these different names, spin density waves, like where the spins are lined up in a wave form, charge density wave, you have metallic states and antiferromagnetic states. So you can have, just by varying the temperature and pressure, or temperature and the chemical composition slightly, you can basically move the same material through all of these different complex phases space. So, and the pressure effects can be very drastic. I call this many phases of the elements on the simple elements under pressure. For example, you take sodium. Sodium is an extremely good metal, and you pressurize it, and it becomes a transparent material that is insulator. And for example, you can take helium, and it's going to, under extreme conditions, it turns into a conducting phase. So on for silicon, it becomes a superconductor, and or you can have the insulator metal transition in molecular oxygen. So things change form, and pressure effects can help us learn about them. Specifically to the topic of this that this group is interested, that are superconductors, are the materials that are essential for quantum computing. There are this graph is showing the different types of superconducting materials. Superconductivity is the state of matter that when you lose complete resistance to transfer of the electricity, so they show a perfect DC electrical conduction, and they also expel the magnetic field from their interiors. And different symbols here are showing different types of superconductors, meaning that for those that we understand the mechanism, or and those that we actually don't have good model. And interesting thing is that from all the symbols that you see here, only the green circles are the ones that we think we have a very good theory known as BCS to explain the physics of these materials. Everything else, we don't have a comprehensive theory for them, and it's essential to have the theory for superconductivity, the universal theory of superconductivity, or theory for all groups of superconductors, different theories that help us to find something that is functioning at room temperature and ambient pressure. And one of the, as you can look at here, that most of these superconductors, they're way below the room temperature they function. This is function of years, basically. And the condition that these materials, they superconduct, which is at extreme conditions, is at low temperature or very, very high pressure. And that makes them not very suitable for application. And the motivation of high pressure studies is that to help us understand the effect, the mechanism of superconductivity, for example, in materials, and or other phase of the quantum effects. And that allows us to find new materials that they have similar properties, but at ambient condition, which is like basically zero pressure or room temperature and ambient pressure, which is slightly more than zero. And that's important for application of, for example, superconductors. So what I'm going to do next is that I'm going to talk about a little bit about the experiments that are done under high pressure. How do we apply pressure? How do we study materials? And then I want to introduce a quantum effects that is less known and less talked about, and that is the dynamic disorders in crystals and quantum phase transitions due to the lattice quantum phase transitions. You can apply pressure by basically squeezing something or exploding it. Both of them, they create high pressure conditions. And this is the basically principles of two subdisciplines or subfields of the high pressure research, which is a static pressure and dynamic pressure. Dynamic pressures are used, are super fast measurements, usually done by explosives or compression by the lasers, or there are different methods, but they're very, very fast. They shock waves, and they create very high density material at a very short period of time. Whereas the static measurements that are done in different devices, the most well-known of them is diamond anvil cell. They can create static pressures much lower than those dynamic pressure ranges, but for a very long time. So you can and you can reach equilibrium in the material. Dynamic, these are the pictures of some of the dynamic experiments that that types of pressure that can be created in dynamic case. The interpretation of data is extremely difficult. It's a rapidly evolving field, and we have lots of places that they do these experiments. Then we have the static pressures, and the static pressures can be done between the tip of two diamonds. It's in a tiny device that can fit in the palm of your hand, and it can create pressures twice as much as core of the Earth, which is 3.5 million atmosphere itself. It can create like 7 or 10 million atmosphere, or 1 terapascal. Reports reaching about 1 terapascal has been reported in diamond anvil cell. So it's extreme compressions, not nearly as close as what can be achieved dynamically. But the thing is that you can put a lot more probes, as I'm going to show, in diamond anvil cell, and you can study your material properties in a broad range of variables. This is the smallest diamond anvil cell that I've seen that was in Seoul, University of Seoul, and it just fits in a palm of hand. And the principle is that you have 2 diamonds, and there are 2 diamonds, and there is a piece of metal that you put between the 2 diamonds. You drill a hole, and in the middle of that, and then you load your sample, your pressure manometer, and your pressure transmitting medium, that I'm going to refer to it as PTM, in there, and trying to create hydrostatic condition. Well, obviously, everything freezes under pressure. Even helium freezes under pressure. So hydrostatic condition, the way that we define it, an ambient condition, under pressure may be a little bit different. It means we call it quasi-hydrostatic. And now the nice thing about this diamond anvil cell measurements is that because diamonds are transparent to the electromagnetic most of the parts of the electromagnetic spectrum, you can look at through the window that you open at the back of the diamonds. You can do a spectroscopy on all various types of a spectroscopy can be done on the inside of the diamond anvil cell. And you can also do x-rays, and you can at the same time you can place leads on top of your sample, electric leads. This is looking at the basically tip of the diamond, and this distance is 0.5 millimeter, and you have 2 samples next to each other, and there are electrodes that are coming measuring the properties of the samples under pressure. And you can do spectroscopy, you can do magnetic studies, we can do NMR, all kinds of different probes can be sent, and we can discover new things about the materials. Now, well, are there any questions or okay, so I want to talk about the exploring.
We have a question. Yeah, we have a question.
Yeah.
It'll be very interesting to hear your thoughts on a material that can be used as a bridge between classical and quantum computers as a bidirectional manager for exchanging data. It's on the chat.
Okay, so let me look at the chat. So it's looking at the interesting to hear your thoughts on material that can be used as a bridge between classical and quantum computer exchanging data. That's a very interesting point. I mean, to be honest, I haven't thought about something that can be between classical and quantum computers. But here is one thought about it. With changing something like pressure or temperature, you can go between classical and non-class and quantum effects. You can you can go to a quantum state of matter, and you can vary the temperature, and you can switch back to the classical states. And I think that would be one way you can go from one material to another state. But then the question is that what could be the bridge between the classical and quantum computers? Typically, the quantum computers, we're looking for so how about something like, for example, pressurized something that becomes a superconductor with the pressure or with the optics, with some methods variable, and otherwise in the classical form, it can be used as also as a in a form of the classical computer in terms of the normal semiconductor. So something that goes from semiconductor to superconductor. So that would be an example. But that's a great question. It's very interesting. So now I want to talk about one one particular material that I think that is super exciting. It's state of matter that we don't know about. And I just want to tell you that many of the things that we do in the lab at the moment, they look like, wow, what is the use of this? And that was the case for lasers. You read early papers about their lasers. They say, well, like it could be some use eventually for this. And same thing here. We find material properties, and thinking out of the box, you are going to come up with very interesting things that can be done with them. So here is the story that I want to tell you about lithium. Lithium is this element, is a third element in periodic table. As you can see, is right after hydrogen and helium. And this is the silly artwork of the helium, if you can call it artwork. This is basically the nucleus, and it has only 3 electrons, 2 in the s shell and 1 in the 2s shell. And it is the first element that becomes superconductor at the ambient condition, as also under pressure, as I'm going to tell you later in the periodic table. It's the lightest element after hydrogen and helium. And for those of you who are familiar with the helium, helium is the material that has 2 quantum fluid states, the only material that never freezes at ambient pressure when you cool it down to 0. Instead, it becomes this superfluid state, 2 superfluid states. So lithium has 2 isotopes, lithium 6 and 7, and lithium 6 is not that much heavier than helium 4, which is a superfluid. Lithium is the first metal in the Oh, you can't hear me? You couldn't hear me? Sorry. So I just wanted to say that, sorry, I'm going to go back, dial back. So I'm going to tell you about lithium. Lithium is the first element in the periodic table that shows superconductivity. And the first, it is the lightest metal, lightest superconductor, and it is the first element with the core electrons. And it's not much lighter than helium. And helium, it is the material that has 2 superfluid states, the only material that shows the superfluid states that has 0 viscosity. There are equivalent of superconductors, but except for the lattice, like, I mean, instead of electrons, it is the helium atoms that are flowing without the viscosity. Lithium 6, stable isotope of lithium, is not much heavier than helium 4. It is metallic state, though, so the physics is slightly different from helium. And the question is that why we are interested in helium, in lithium, from experimental point of view. Lithium is a super simple stuff. It's a book example of a material with a very simple Fermi surface, electronic structures. It has a very simple structure, atomic crystal structure, and you can even assume that it is an empty lattice model. Basically means that electrons, when they move in the lattice, they don't even see the lattice. You can ignore the fact that the ions exist. Now, under pressure, everything changes about the lithium, and I'm going to tell you and it becomes a very complex material and very interesting for the studying the quantum effects, the specific ones that I'm going to talk about here. So I want to talk first about one idea in high pressure, because I know this group are not a high pressure, for sure. Everyone is probably not a high pressure person. So one of this idea is that in this picture, I'm showing that you can pack things really well when you put them in some kind of order. If for certain geometries and for certain shapes, when you are dealing with the symmetric shapes, when you pack them, you are going to end up packing them really well. And when you can't pack them any further, you can apply pressure and pack them further. So in that sense, order packing and pressure, they go hand in hand. And when you apply pressure, also things, because they want to pack better, they come into order. And order is something that we call it in crystalline form. And solids are the crystalline form of them, they're ordered phase, whereas the liquid is disordered. And this boundary between order and disorder is basically it's the melting line. And classically, you are as you increase the pressure, because you want to pack better, things start staying more in ordered phase, and you expect this melting line to go to it persists to higher temperatures. Now, what happens in case of the hold on a second, there is issue here, so let me see that. Yeah, so what happens in that, and for that I have to stop sharing, and I'm gonna move to this region. Sorry, I have to go to a couple of a slide back. And there is I'm going to stop sharing again. So this is, so the way that we explain the melting for the melting is through this Lindemann criteria of for melting, that is basically when your interatomic distance becomes, as you heat the materials, the thermal vibrations, the amplitude becomes larger, and at some point when they become close to the comparable to interatomic distances, you are going to get to the basically the melting temperature. And one of the things about the lithium is because of its lightness, it falls in somewhere between classical solid and a quantum solid. In a classical solid, this is a two-dimensional model of a solid. You have, these are the ions, and they're sitting on the lattice sites. And you see that there is this de Broglie wavelength, that is the quantumness of a material. The Broglie wavelength, you can assume for something like electrons that are super light, they're always, there is a hands up. I mean,
Yes, there's a question from Jordan. What makes helium-3 superfluid so appealing for topological qubits? Is on the chat.
So superfluid helium-3 is the only material that we know that has this triplet superfluid state. So there are speculations for some of the superconductors that people think that they are triplet superconductivity, but we don't know basically any other example in nature. And superfluid helium, even though it's not an electronic state, but it has the triplet. It is the superfluidity is not is not a conventional superfluidity like the helium-4. So basically, you have helium-4, which is a boson, and helium-3, the nucleus that is fermionic, and you have it's because of that superfluid helium-3 is very appealing, because it's resembles the closest that we can get to the topological superconductor, is a topological superfluid, I would say, maybe, if I'm not misspoken here. Does that? Yeah, okay. So that's because of the how unusual the properties of liquid helium-3, superfluid helium-3 is. We don't have, for helium-4, we have Bose-Einstein condensation. For helium-3, we have to sort of come up with. So that's why it is for the topological, in terms of the topological state, this is the closest that we have in nature that we know of. Great question. So anyway, so we have the Broglie wavelength, that is a measure of the quantumness of a material. It shows that how much delocalized is basically you have the ions, or any particle as a matter of fact, is when it's confined. And in a quantum solid, like helium and hydrogen are the examples of that, this de Broglie wavelength gets comparable to the interatomic distances, which means that it starts contributing as the lattice acts as quantum lattice, whereas in the classical solid, the lattice acts more or less classically, and these are the electrons that they all act like waves and quantum mechanical waves, whereas the lattice in the form of solid acts as a classical solid. Because of this expansion, because of this larger Broglie wavelength, for example, in a quantum solid, you are going to have the lattice expands. So you have lattice of helium and hydrogen, and they expand to prevent the overlap of the hard cores. And there was a parameter called as the Bohr parameter, that is a ratio of this delocalization of the ions to the interatomic distance, that was defined for quantumness of the hydrogen and helium, and it basically adds multiplies as a factor into the kinetic part of the kinetic energy of the Hamiltonian. And it was shown that, and it has number of things like this. H bar is like basically this is the Planck constant, which is a constant. R is the interatomic distance. Mass is also the mass, and the potential that keeps things together. And the potential changes by distance, is ratios by distance in a crystalline material, for example. And mass, of course, the smaller the mass is, the larger the quantumness is going to be. That's why we are looking for something like lithium. And that's why helium is so interesting, because it has such a small mass. But it also, helium, even though it's heavier than hydrogen, is more interesting because of the type of interactions that also it has at ambient pressure. However, the interesting physics of helium goes away as you pressurize it. So as you pressurize it, helium very quickly crystallizes, and it's no longer that superfluid state that we know that is also interesting for the quantum computing, for example. However, there are some sort of phenomenological thoughts and ideas that if you have a case that this potential, interatomic potential, is a very long-range potential, which means that this n is a small number, and per se we can say less than 2 in this case, you can see the case that the quantumness increases as you lower as you pressurize the material, which means that you bring the atoms together or make the R smaller. So basically here the variables are R and epsilon and M. M goes with a low mass, epsilon and R, they both depends on, you can adjust by the pressure, the interatomic distances and the interactions. And if you manage to get to the condition, you have a material that has a very long range interactions, you would be able to create that superfluid state at high pressure. Instead of getting rid of it, you can create that superfluid state under high pressure. And that is that enhancement. And this is a theoretical work that has been moved forward for years and years and has not been visualized in laboratory yet, partially because our high pressure techniques have been lagging behind, and we are moving forward and getting all of these new methods to study materials now and reach those high compressions. But the question was posed that can we enhance the lattice quantum effects of a metallic system under high pressure? And can we end up with exotic states of matter? Can we get something like quantum melting? I have to say here that, for example, for helium, both cases of helium-3 and 4, the transition from the normal classical fluid helium below this lambda point to the superfluid is a quantum phase transition. It is a transition that is only driven by the quantum zero point effects. And we can, it's a very exciting field that we can get to, that we are exploring. This is basically the idea. And I did say that what is the classical melting? That's a toy model for classical melting. And in another word, whatever I was saying, you can also envision that if you have your uncertainty principle, if the ratio of the Broglie wavelength to the interatomic distances becomes comparable, then you get melting, but this is now quantum melting. And this picture was proposed by, there is a good review by Sergei Steshov in 2001 about the two scenarios of the melting of the material. These are normal crystals with the short-range interactions in B. And in figure A, you see the influence of quantum effects on the Coulomb type interactions or metallic states, or that is going to be where you are going to get very long range interactions, I would call it, that you can see the quantum melting, that you're going to have a fluid at 0 temperature, but at high pressure instead of at high temperature. So this is basically wrap up of the difference between the classical solid and the quantum solid. And it brings us to say, well, okay, hydrogen and helium, both of them, they have they are very light, but the issue with them is that they are very short-range interacting systems. So the quantum effects, they die off. In hydrogen, actually, for metallic hydrogen, it's predicted that it may have a quantum fluid ground state. But the easiest thing to learn about these quantum effects is lithium, which is a very light element. I'm sorry for this has been distorted somehow in this presentation. So you can see this is lithium. It is the lightest element right after hydrogen and helium. It has a long-range interaction. It's already a metal. So it would be interesting to explore the quantum effects in lithium. So one would ask that, well, you get lithium is cheap. You can get lithium from anywhere. You apply pressure and you get the quantum melting. Well, it's not as easy as one would think. And the issue with it is that we have a lot of phase transitions. The electronic effect comes into effect, and we get a lot of structural phase transitions in lithium. And here is the phase diagram of lithium. You can see as applying pressure, and this is like a 1 million atmosphere, roughly 100 GPa. You are going from phase transition to phase transition to phase transition. As you go to the lower symmetry phases, even in the classical materials, you get to have the, you are going to get the melting temperature going down. The reason for that is that imagine that you are trying to pack a bunch of spheres in a box, and if you go to higher packing orders, you are going to basically you are going to pack them better. So my original naive example of packing better with order would work. But if you want to pack chairs that in a material in a room, you may be better off to do this with disordered system rather than packing them very in ordered state. So this departure, that is the electronic effect to lower symmetry phases, leads to this basically lowering in the melting temperature. That was debated that it could be also having a lot of quantum effects due to the quantum effects. But we have done these studies, and in our group, and there were other groups, we have contradictory results. And the issue is that there was no conclusive evidence of quantum melting, even though we see this low melting temperature, which is around room temperature at 500,000 atmosphere, where hydrogen, for example, melts at 1000 Kelvin. And you can see this low melting, this structural phase transition to lower symmetry phases in all alkali metals, even those that are super heavy. And consequently, you can see that they all also have this low melting temperatures. These are much higher than lithium, but still there are low melting temperatures. They're all in centigrade, except for the potassium here that has like around 400, 450. Okay, but you see this melting that is not quantum effects. So we have to go around a different way to explore the quantum effects. And for that, what we have envisioned is that if you want to look at this, the Bohr parameter, the increase in the Bohr parameter, we cannot just go measure a property and say, wow, this is very low melting temperature, it must be a quantum effect. We have to look at different logic. And one thing that we thought is going to be very helpful is look at the isotopes. And isotopes of same material, they're electronically similar, so you can exclude the electronic differences and only mass difference. And luckily for low Z elements, low Z number, no atomic number, hydrogen, there's 50% difference, helium, there's 25%, the lithium is 15%, and beryllium is 11%. They have a lot of differences in the mass, and you can probe these through the isotope effects that are unconventional. And the idea is that you also want to get rid of the thermal effects, and because there you get the phonons, and low temperature properties are ideal. And people have studied the low temperature properties of lithium, number of the low temperature properties, and they have seen various effects. One of the things that I want to highlight is the study that we have done in our group, and that is about the superconducting properties of the two lithium isotopes. So you have a normal superconductor. This is the superconducting property, the black curve of lithium-7. That's the most abundant isotope of lithium. And in a superconductor, the transition at critical temperature is going to be in a BCS type, conventional type, that lithium should be one of them. It goes at 1/square root of mass. So for lithium-6, you would assume that this is going to be simply following this linearly. However, when we did the measurement, and that would be what we speculate lithium-6, the red curve, is going to be, we saw a completely different thing. We see the lithium-6, the transition temperature goes ups and down, whereas lithium-7, shown by black, it's all going up. So there is an anomalous behavior. And we did these measurements very carefully. We put both samples next to each other in the same pressure chamber and everything. So there is an indication of the presence of the quantum effects in the properties of the lithium that comes from at low temperature. And we wanted to explore these. And for that, we needed to understand the structure, the crystal structure of material under pressure. And this is something that we have done. The crystal structure of lithium, we looked at this region and also this other region, all the way to 500,000 atmosphere. And the first region was this region that there is this strange phase transition that happens on lithium. And it is going through this, even as you cool it down, it goes from a simple BCC, that is the cube with the one atom in the center of the cube. It goes through this martensitic transition to HR3. Actually, this is mislabeled HR3. And we wanted to see the boundaries of this phase and the isotope effect. This is a complex phase. This is HR3. This is how it looks like. It's a stacking fault of the FCC and HCP. And thermodynamically, according to calculation, shouldn't be even there. So when you cool down from BCC, you should end up with the FCC, but not this 9R. This happens at much lower temperature. Well, we looked at this, and the issue, we wanted to understand the boundaries of this, the ground state of lithium, and understand if the quantum effects contribute to the phase transitions of lithium, and if the superconductivity relates to the structural phase boundaries of lithium. And the issue is lithium is super invisible. It has only 3 electrons. You can't see it with X-rays easily. And we are dealing with the samples that are super tiny in a diamond anvil cell that is like say 20 micrometers or so in a linear way, linearly. It's very hard to observe them. And and then with neutrons also, and there's another way of looking at the lithium neutron experiments in diamond anvil cell were very difficult, just recently become possible. And also you can't do it on lithium-6 because it absorbs the neutrons. So this is a real picture of a diamond anvil cell and the measurements that we have done. I'm not going to go through these graphs because I think that's going to be boring. I'm just going to tell you the story that this is an ambient pressure study, that when you start from BCC lithium, cool it down, it goes bam through this BCC martensitic. When you warm it up, it goes through BCC, martensitic, and FCC, and then it becomes BCC and FCC. It seems like there is something weird going on here, whereas you cool down, you go from state A to B, but you warm up, you go to state B to state C, and state C is supposed to be, to begin with, to be the stable structure. So it looks like that there is a reason for this to happen, because this warming is like similar to what theory predicts. Cooling is not. And under pressure, we did the same thing, and what we found is that exactly the same thing. You cool down, you go from BCC to this HR3, and you warm up, and you can see that you don't go back to the, you don't go back, you start producing the FCC, or the what theoretically we think is the ground state. So when we go here, again, another graph, we go from BCC to FCC, and the thing about is that was hypothetical phase boundaries, but we found out that this phase boundary is wrong. We found that from BCC, once you go to FCC, it's not going back to the FCC, and plus when from BCC to HR3, when you go back, you create, you are going to, you are not going to create back the, when you go from BCC to FCC, you are not going to create HR3. And we did X-ray on this material, and this is the phase diagram. So that is BCC structure, the ambient condition structure. You cool down, and it goes to BCC and martensite, or this 9R. But then when you cool down from BCC and go to FCC, FCC never becomes this thing. So we showed that these boundaries are wrong. We clarified that this is the FCC, but this is not the most interesting thing. The most interesting thing is that we looked at the isotope effect. And what we saw is that when we cool down lithium-6 and lithium-7 through the same similar paths, you are going to find out lithium-6 actually to lowest temperature shows this BCC remains BCC. We don't see this martensitic transition. And the boundaries of these two are different between the two isotopes. The solid boundaries are different between the two isotopes, which means that we found the low temperature property of lithium that depends on the isotopic mass. And the only other material that we know that has the isotopic mass dependence on the solid structure boundaries is helium. Helium-3 and 4, they show the two different types of superfluids, but also two different types of solid boundaries. This is solid BCC, this is solid HCP for helium-4. So there are quantum effects that are in fact that we can see in case of the lithium. So that is one thing. The other thing is that we showed that this HR1 should not exist altogether and is not the ground state or the lowest energy state. And with that, we just basically, instead of cooling down, which always produces this phase, we pressurized, cooled down from the FCC and backed up and warmed up. And we never generated this martensitic phase. And that is the thing that I was trying to say, that you can create metastable phases, and you can, with exploring different paths in the pressure temperature phase diagram, you can synthesize new states of matter. And they can become stabilized differently. And we did that here. And we showed both for lithium-6 and 7, the FCC structure is the ground state at ambient. We basically had this red symbols are showing the BCC structure. We go from 0.3 pressurized, we produce FCC, cool down, FCC, back up, and passing by the boundaries that they were supposed to happen during normal cooling, isochoric cooling would create this HR3, we would find out that it stays in the FCC. So we synthesize the ground state through the alternative paths. Okay, so the explanation we have is that just like similar to our GPS, the fastest route versus the why do we get, the question was remaining, why do we have even this basically this phase being produced when you cool down? And that is because of the kinetic effects. You have the FCC, BCC cooling down, lithium is unstable. It should get to another phase, and that phase should be FCC, but that transition is slow because it's a diffusive transition. And the fastest transition is martensitic, which is, I call it, is like avalanches, like planes are falling down. And the fastest route is what your GPS gives you rather than the shortest route that may consume more energy, basically. And in this case, this is a cartoon that I'm showing that you have the BCC lithium and you cool it down. These are the states, energy states. FCC is lower energy, but it's going to be harder to get to. And martensite is the lowest energy, and it cools down and you get there. Whereas when you are pressurizing, take a different route, and you pressurize, get to FCC, and then try to go back, there's no reason for FCC to go to a higher energy state. It just stays there. And same thing is happening for lithium-6, except for in lithium-6, this difference between the energy of the martensite and the BCC due to the quantum effects are negligible. So the sample stays mostly in the BCC state all the way down to lowest temperature we measure. So the last part is the electronic properties of lithium. This, like, again, materials show weird behaviors. This is a work that was done by Neil Ashcroft in 1999, and it shows an unusual character of an electronic structure that may lead to condition of the superconductivity in lithium. And later on, the superconductivity was found. But the interesting part is the localization of the electrons. Electrons can localize in the lithium lattice and form these quasi-molecules even in some predictions. And these are very interesting states of matter when you have the localized electrons without a core. And we wanted to understand the superconductivity of lithium. So we needed to focus on this pressures of the superconductivity. And one of the issues with this superconducting region is, again, the ambiguity in the structures, crystal structures of lithium. And you can see these are two different measurements done by two different groups. There is a phase that exists in one and is not existing in the other one, that low temperature. And in our recent work, we have basically looked at this phase as well. And this is essential for understanding the complexity in ups and downs in superconductivity of lithium. And that this is the phase, this is the TC of lithium as a function of pressure that goes up and down. And what we have done is that we measured this, and here is that we found that at 15 Kelvin, that is the lowest temperature we could get. This phase that is HR1 exists, that was ambiguous. And using the theoretical calculation, we can show that this is the theory that our colleagues at University of Buffalo, they have done. We can show that how the superconductivity changes by pressure, and if you assume the right structurals in the lithium. And more interestingly, we also found the two isotopes of lithium, the boundaries of this phase, or HR1, shifts by 1 GPa. 1 GPa is a huge amount of pressure. It's not in our world of high temperature pressure superconductors, but it is a very high pressures in normal world. I mean, 1 GPa is 10 times more than the bottom of the deepest oceans, or super high pressures. So it is shifted. So we see a shift that is consistent with previous superconductivity experiments. And so basically, we show the phase boundaries. We understand the quantum lattice effects that still exist even at higher pressures in lithium. And here is two other new predictions and that are for the lithium. And those are, one is the emergence of topological states in elemental lithium under pressure. We need to get to really high pressures of above 200 or 300 GPa, which is completely feasible. And then it can also form the topological semi-metal. And these topological states, as you know, are extremely important for quantum are important quantum states of matter, and they can have a lot of applications. I don't know, in the context that we think about the quantum computing nowadays, what would be the application of these, but they can open up new ways of thinking about the quantum states that can be used in general. So this is what I have, just like basically a bunch of, and I wanted to thank a group of my collaborators that they have helped me with, and I helped them, and they helped me to get these work done on the understanding of the superconductivity and the quantum effects in the simplest of the metals. And what I hope that I could show is that how complex even the simplest materials are, and how you can take advantage of these high pressure effects to address those. Thank you. So I see a question. Is doing these experiments, how much concern is taken of the effects, if any, of materials which make up the devices used for the experiments? Is there any electronics or that from the device. So you mean that when we measure, if I understand the question, is that our measurement, how our measurements can be affected by the method of measurement, how the property that we measure can be misled? Is that the question? If you could clarify the question, yes, okay. So that's a great question. Yes, there is a lot of errors that can happen in high pressure experiments, and you might have been familiar with some of the recent errors that have been happening, and common things that and generally in condensed matter. So here is what we do. Number one, if you saw that we have been using a lot of different methods to study one thing. We use like crystal structure. So if we are measuring something that it looks like metallic or superconductor, but crystal structure shows that it is, it can't be. We can do the band structure. We know the crystal structure, and if you see that there's no way that this can be a superconductor, or we know that we have to go check back. In terms of the electronic properties, we we have methods that remove the leads, the measurement device from the measurement path, as a normal 4-probe or Van de Paa method, that you have basically you make the measurement in a way that you isolate your sample from the wiring, so you don't see the effect of wiring is diminished to almost zero. If these measurements done right, you measure the right thing. But there is a lot of room for device errors, that systematic errors of device error, experimental errors. So are these experiments better done in virtual environment? Yes and no. So we do, as you saw, we do collaborate with theory, and we try to do this virtual experiments basically in, but no, because every theoretical work relies on some input, and those input may be inaccurate. What I was trying to show you here is that the quantum effects typically, quantum lattice effects are typically ignored altogether in a calculation. Quantum zero-point effects, even those that they're putting in, they put them by hand. There are so many states of matter that we can't think of. If I would have told you, I say that something becomes superfluid, and whereas you didn't know about it, if somebody would have told me, I would have thought that it's science fiction. So, but things do happen. We can't, in the virtual environment, it needs the collaboration between the two is needed. You cannot, you cannot take into account all the effects in virtual environment. There are many new things that we find. We still don't understand the high TC superconductors. There's no virtual environment that can understand the high TC superconductors, but they exist, and they have been existing since they have been discovered since 1985 or 6 or so. We still don't have a theory to explain them, so we need experiments. Yes. So I hope that I answered that question.
I have a question. What is quantum melting?
Oh, quantum melting is, so basically that is the phrase that I use, that normal melting is thermodynamic melting is happening because of the phonons, because your lattice falls apart because of the increase in the vibrational amplitude of the atoms, and becomes disordered, and you have the melting. Now, quantum melting is not driven by the phonons, but zero-point effects of the lattice. So quantum mechanics tells us that if you confine confine a particle, it's going to have a non-zero ground state. The energy is going to lift up from the zero, and we call it zero-point energy. And that zero-point energy can lead to a material that is not going to be have a state. If the quantum zero-point effects are very large in a material, in any condition, it can be ambient condition or in a dense form of a material. If they're very large, in that case, the lattice cannot be stable. The material becomes disordered. It becomes it's basically it melts. So that is quantum melting. It's a transition that is driven is because of the quantum effects. It's not because of the is not because of the it is not because of the classical effects or phonons. It's because of the 0-point effects. So did it answer the question or?
Oh, yeah, sure. Yeah.
Awesome.
Thank you. And also, we have other question. Effects of gravitational forces, are these experiments better done in zero gravity environments?
That's a great question. That's why we need a space space explorations. Yes, yes, those are if you want to get rid of the gravitational forces are very, very small, but we typically ignore them and the gravitational forces. But they're super small in small distances, and we assume they're negligible, but that's a great question. We have the experiments done in zero gravity environment, and some of these experiments are going to show the differences that can make. But I assume, or at least we assume, that the gravitational forces are negligible in very short distances and low masses. So.
And I also have another question about the terminology. What is the classical solid and quantum solid?
Yes, that's a good question. So classical solid is a solid that, so there was a, we know that, for example, light is, most people are familiar with the fact that light is particle, can be described as particles, photons, and it can be described as also waves. And then wave nature and particle nature of the light is something that was initially found out. And in fact, Einstein got his first Nobel Prize because of the description of the photoelectric effect that precisely explains the particle behavior of the light. Now, later on, de Broglie also found out that materials, like, what we think of as matter, like electrons or protons and light materials, they also can behave like waves, and define the wave length for them called the Broglie wave length. And this is the Broglie wavelength depends on the Planck constant, and also inversely to the momentum, to p, and which is basically the Broglie wavelength of the material is how delocalized. If it's a wave, it's going to be delocalized. And how delocalized is something. For something big and heavy, like the lead, for example, nucleus, you can assume that the Broglie wavelength is super small, and you can see it's classical. It means that it looks like one single particle. Now, if you have something like electrons, you can no longer assume that it's like one single particle. It has this dual nature. It becomes very evident. So both wave and particle behavior becomes very, very obvious. And we always assume electrons are having both. So we may think all of the properties that we know in the solids are assuming the electrons as waves. So now, what is a quantum solid is that for most of the solids, you assume electrons are quantum mechanical, which means that they're like light particles. They are dual nature, wave and particle, whereas the lattice itself, which is the nuclei, because nuclei are so heavy, much heavier, even the lightest one of them, which is hydrogen, is going to be 1,000 times heavier than an electron. We assume that those are classic, which means that they are just acting like single particles. And in case of the quantum solid, that assumption is no longer a very good assumption. So for example, and those are hydrogen and helium, they are the quantum solids that they're delocalization of the wave function of the nuclei is significant. It's significant enough that impacts the properties. And what I was trying to show here is that lithium is another example of a material that shows quantum solid behavior. It is a solid that is not bound by the lattice is not bound by just the classical. You cannot assume the lattice is classical. You cannot explain the properties. In case of like hydrogen, you have these rotons. The hydrogen atoms, they rotate freely even in the lattice. So that's just basically one of the examples of how the properties of something that is super light can be different from even in the frozen in the solid phase, can be different from the classical solid. The melting temperature is super low. Helium never freezes at ambient pressure. Hydrogen freezes at very low temperatures. So all of these things, they are the quantum effects coming from the basically large 0-point effects in the nuclei, not just the electrons.
Thank you for your answer. And at the beginning, you mentioned you use the crystal, the diamond crystal to do experiment, but diamond is too expensive. Can you choose glass or something cheaper?
The diamond is the strongest material in 3D that we know of. You cannot use nothing else. People have tried to use moissanite and cheaper crystals like quartz and everything, and none of them, they can withstand those pressures that diamond can withstand. And as a matter of fact, I mean, glass is not going to work altogether, but as a matter of fact, for example, if you use something like a moissanite or quartz, like quartz not really is not going to work for even for very low pressures, but those crystals are going to break in moderate pressure. So if you want to do even low pressure experiments, often it is cheaper for you for a long lifetime of a laboratory to use diamond because they won't break if you use them at low pressure. Under high pressure, they break. The high pressure experiments are very expensive though, but they allow us to find a state of matter that we are trying to find out. One of them is topological superconductors. At ambient pressure, may be very difficult to find one, but when you expand your horizon, you add another dimension, you may find it might be easier. You have access to a lot more materials. So just the fact that we need to be able to diagnose them properly.
Thank you. So are there any other questions? So please feel free to unmute yourself and ask a question online. There's another new question. Are the coherence times of materials being studied under various pressure in addition to the phase transition properties?
Yes, you can measure the coherence times of the materials. For example, you can think of the magnetic materials, and you can use NMR for measuring the coherence time. So you could, yes, there are various, and if you clarify what kind of a coherence time you are thinking of, it might be easier for me to I may be able to provide a better way of saying that coherence is it, but yeah, you can do the time-dependent studies. And have you looked at the experiments done at Heated Lab at York University in Toronto? And not actually, I mean, I'm not sure if I will look them up. Are they related to the to what I was to this work? I would like to I would check it out. I would check them out. Yes, Professor Simon. Yeah, okay. No, I have not seen this work, but I would definitely look it up, and that is Thank you for the suggestion. Yeah, I see that is a new study. And for any of these new material properties, high pressure can play a fundamental role to add to what we understand, because you have a material at ambient condition, you apply pressure, you change the interactions between the atoms, you modify the interactions, and you learn about it. And you can verify what you think is and we are studying in my group many of these layered materials. They're specifically very interesting under high pressure because they have the layered material. One of the properties they have is that they usually, or two-dimensional materials that are, they have this very interesting property that they are anisotropically compressed. So you can interact typically between layers, they compress more substantially than within the layer. And that leads to tuning the interactions very effectively. So that's something that pressure is a very effective tool to take materials from one state to another. So you can make something that is, for example, magnetic, turn it into superconducting under pressure, and vice versa. So that there are like high temperature superconductors under there are by pressure or by doping, you can change the ground state of the material.
We have a good comment. Work talk, learn a lot, and now have a lot of more questions to move over.
Thank you. Thank you so much. I'm glad it was helpful.
Yeah, and other question is, what is your future work in terms of the research?
So one of the things that we are interested in is that, well, as physicists, we are interested in simple things because I don't know if you've heard this joke of the spherical cow, that we always turn things into simplest form and simplest model. For us, materials that are simple are like gems because we understand them better. And if this has a very simple electronic structure, it's like helps us a lot to learn a lot about. We are interested in pushing like lithium physics to terapascal, which is 10 million atmosphere region. Lithium is not understood about 1.5 million atmosphere, and that's because it's super hard to deal with. And it is our goal to push it to those regions and better understand these quantum effects. Hopefully, we can even find evidence of the quantum melting, quantum fluid ground state in lithium, in hydrogen, in super light elements. Meanwhile, we are also very much interested in exploring the quantum effects in the materials that are like in like quantum phase transition driven by electrons. It's basically understanding this correlated electron system, magnetic systems, superconducting systems are very exciting for us. If we can, so there are I would say two parts of my laboratory. One is working on quantum effects in lattice dynamics of the materials, very low Z elements. And the other part is looking for the superconductors and high temperature superconductors and helping to understand the phenomena of superconductivity in materials that are complex and are not well understood using high pressure techniques.
So which laboratory or which facility provide you the equipment to do all those experiments?
So we have, and we are doing some of the experiments in the, we are doing some of our experiments in the our own lab. So we have like cryogenic experiments. We have the capability of doing magnetic susceptibility measurement, capability of doing transport measurements in our own laboratory in diamond anvil cell. In addition to that, not every experiment can be done in the laboratory. We work in Argonne National Laboratory in high pressure facilities, HPCAT and JC CARS. We collaborate with CDAC, is a collaborative group that they do the diamond anvil sort of stuff under pressure for crystallography. We work with National High Magnetic Field Lab to do high magnetic field, because part of the studies that I didn't show, I just wanted to show one example that we did was on the understanding the electronic structure of lithium. We did Fermi surface fermiology measurements in lithium. And thank you so much for the references you're putting them. There are we do collaborate with various labs, and we do neutron studies also on Oak Ridge National Laboratory. And we also collaborate with other groups if you want to reach, for example, lower temperatures that we typically do. We have like a helium-4 cryostat. We get to like 2 Kelvin or 1.8 Kelvin on best conditions. But we can, if you want to go below that, then we need to collaborate with other groups.
Do you collaborate people in Argonne lab or Oak Ridge lab that so far apart? You're in Utah and they're in Tennessee, and other is in Chicago.
Yeah, so usually, I mean, we travel. So we, as a group, we ask for beam times. We travel there. Sometimes when the collaboration is established, we just have a collaborator there that we ask them to do the experiments. We just send them the samples. But so far, most of our experiments, we just have been traveling there, staying up 48 hours and running the measurements. These are very difficult beam times to get access to. They're open internationally, so that's great. Yeah. So there is a question. I said, can you talk about annealing and varying several physical pressure, temperature, magnetism simultaneously? Yes, we can measure. We can vary pressure, temperature, and magnetism simultaneously. We can do all of them together. And we can also annealing is extremely important. Part of that recovering, that showing that the FCC is a ground state of lithium requires annealing. You can't just press something and get somewhere and say, this is the state that you're landing in. Annealing something helps relieve the stress and getting it back to the most stable structure. Yes, we do annealing all the time. Yes. Great point. Yeah. But we can do that. I mean, we have the temperature, magnetic field, pressure. We can also apply other, like, I mean, we can vary for measuring, for example, conductivity. We always routinely lower the temperature, and we also measure increase the pressure at low temperature. We can increase and decrease the pressure at low temperature and control all of them simultaneously, and the same thing with the magnetic field. And the technology now is really going fast. We are learning so much. And one of the things with the issues that we had was the volume of data that we are getting. And now with AI, we're hoping that a lot of mysteries in high pressure is going to be very quickly come to resolution, resolved, because AI can help us. For example, when we take all these data points, AI can look at massive number of data points, and without us sitting and trying to fit, just do it very quickly and more efficiently and help us navigate the path forward.
So have you applied generative AI in your experiment yet?
Not yet, but that's the goal, how to actually use them in data analysis, and it's gonna be tremendous help, because human eye, and we can discriminate. We can stop seeing what we don't want to see and only see what we want to see. So, and that leads to that the human error is very difficult to get rid of. It's great that we have the human error, because it's our intuition. We know we can extract information from data that looks nonsense to many, and then with further experiments we find a real prove them many times, but also the same intuitive behavior can lead to mistakes. So AI can be very useful. We have been speaking about when there is a next generation of the synchrotron and advanced photon source, there are a lot of discussions about using AI to help users doing their measurements.
Yeah, got a good comment. Thank you very much. I learned a lot.
Yeah, thank you so much. Yeah, I'm
It's another question, but
in
insofar as these were previously unknown property of lithium under pressure, wouldn't that limit AI's capability to predict behavior?
Well, AI needs input, so it builds based on what we based on the models that we just like us. I mean, it's not gonna. We were thinking everything should be classical until it turns out that things don't behave classical, and quantum mechanics came around. We thought everything is acting classical till relativistic physics came up, because we saw evidence in the nature that it behaves differently. So nature has a behavior that AI needs to know to predict. So there are many, many ways that nature could have been, but it is in a certain way. AI can help us just like us based on evidence. So AI is not going to replace the experiments. It can predict things that we may not think they are there, or it won't occur to us based on, like, for example, based on the existing models. It can predict in a new material that we couldn't think of and say, well, okay, I looked at all these series of materials, and based on this physics, this one is a great candidate to show this behavior, and you test it and say, wow, it does. But it's not going to predict new physics. So outside of so a lot of times, unless we believe that we know everything about the nature and there is nothing new that we can learn from it, we have all the models, and all we need to do is basically a big box of Legos that we can build anything with, and we have all the pieces, then AI, I mean, if that is the case, yes, AI can help solve all the problems. If not, no, and I don't think it is the case. I think we are learning a lot about the nature, and there are things that AI cannot predict.
Wow, we have 3 questions. First one, can you simulate experiments on the computer and model them as dynamic systems?
Well, I'm not a theorist, but yes, you can. It is very difficult. If you look at the number of the particles that typical theories, the quantum theories, or like I'm in quantum simulations and stuff using, but like they say, wow, we use like 1,000 particles. And I mean, to us, I mean, 1,000 is not enough. So I think Phil Anderson had this famous quote that was saying more is different. So I think a lot of complexity of the systems comes from a larger number of particles. And I think that eventually we could, and quantum computers are going to help us to do larger simulations and stuff. But at the moment, it's a very difficult thing. So to simulate a real dynamic system that exactly finds all the, I mean, does what the experiment does for you. So AI can extrapolate from experimental result, but not elucidate from a known behavior. That's right. That's exactly what I meant to say. You wrote it better than I could say. It's interesting how AI will play certainly useful as a tool, but not as it limits or needs to recognize. Yeah, this is really something that we learned in the past century. We thought we know everything. We were sure that the class physics was complete, and you have to just collect the stamps. Next, the art was that, and this nature showed us very different things. There are so many mysteries we don't know, and yeah, where are those dilithium crystals when you need them? Yes, that's right. Yeah.
Should autonomous AI experiments or AI for data analysis inferences or both? There's a
Okay,
question.
autonomous AI experiments or AI for data analysis and interference, or both. So We haven't looked at the autonomous AI experiments yet. That would require also developments, I would say, in robotics. That would be that can happen, and then but we are more thinking about the AI for data analysis. That is something that can be super helpful because it can look at the face space, is not going to get bored, is not going to get frustrated with messy things, and is going to put things in an order the way our human minds have trouble with. Explain puzzles like the graphene magic angle. So that is something I think it probably AI can help modeling with those kind of things. If there is new physics in it, though, no, it can't. So we are still thinking there are a lot of new physics that they might be in some of these materials and material properties that we see. But I mean, for example, I mean, I think robotics and AI are going to take us to the next level. We are going to see a revolution in quantum physics and in modern physics in general. And in it would be, we need, I think, the quantum physics, AI, and the other like aspects, robotics, and all of these are going to help us. There is a question. You mentioned annealing. Can that be done in gradient descent in milliliter? Is it all about finding the low energy point? Well, I actually don't know the answer to this question for the gradient descent. Let me. So this is more theoretical approach, right? So annealing, what I meant was more experimental annealing of materials, and it is done in the theory too. I think the equivalently you can do this to relax the. I thought is more like relaxation. They relax the lattice. I was familiar with. I think that's the that's one of the things that's going to be. And how to design quantum new materials. Yes, that is definitely AI is going to help us, because the way that we do this is that now we just look at the materials, the trends, and the trends are something AI can do better than us. Like looking at the large data set, and we miss a lot of things. Like there have been always sort of serendipity type of discoveries that they shouldn't be serendipity. And I would assume that if we have the autonomous AI that allows us to do things faster, our material discovery is going to go to a really new level. And there is so much data unanalyzed that are stored on every national lab, every laboratory, that we just throw away. It's not looking good. It's not looking good. And AI can, I'm sure, can extract so much information out of those.
So do you use any AI tools or software for your experiments?
Not yet, but we are going to use this in the Argonne National Lab. One of the things in the upgrade that they have now, they're going to be 4th generation synchrotron, and there are going to be a lot of data flux, and for handling those and making it more efficient, there is serious conversations and efforts to make this AI based. And all the universities are also basing on your own trained, sort of AI work. I mean, a lot of people are trying to have AI microscopes, AI systems that they help us. So I think that's just a matter of time. We're going to see that revolution happening in 2 or 3 years.
So basically, it's using hardware in AI, not the software.
Both. I think both of them are going to be useful. Initially, it's going to be software because we have so much data, and here is in a chat is same data problem in astrophysics. Exactly, we are using like citizen scientists. People sit down and try to pixel by pixel look for things, and people miss things. Some people see things. AI can do all of those things. So and we can basically take advantage of what we have and analyze all of those and reach, maybe we learn, it helps us maybe to learn new physics from what we already have. So we may see trends that we didn't know they were there, we weren't paying attention. We may see those from existing data.
See.
So I got a lot of questions here.
So for the software, so the Argon Lab developed the software, or
They are trying to develop the software. They're working on it. That was just like, I mean, I think they're going to have it when the Deemyad line is back up. They're trying to help like develop ways that we just basically analyze the data while we are at it, because the way that it works, that you go there, you take your sample, you do a preliminary look at the quality of the patterns that you receive, and then you decide that it's a good sample or not. And many times, this is a mistake. This is just basically you're throwing away great data, and you are throwing away something that is actually more helpful and useful because you think it's noise or it's bad, it doesn't look good, it's not what you're looking for. It's the more interesting thing, but we don't think right at spot when you are measuring. So AI can look at those, and maybe some of these events happen over and over. For example, I was doing this measurement with lithium. When you do measurement in lithium and diamond anvil cell, about 20 gigapascal, lithium attacks diamonds and breaks them. So you have to keep it at low temperature. You have to do coating on top of the diamonds, and the attacking of the diamond is something everybody worked with lithium knows. Diamonds are expensive. It's like over $1,000 each diamond, over $2,000 experiment that is failed with lithium. So then I was in Argon, and we were so worried about the lithium reacting with the diamond. And one of my students asked, but what is lithium actually reacting with? I said, I think it forms lithium carbide. So why would it happen at 20 GPa though? And that's a question we still have to answer. So that interaction, sometimes we just try to avoid what is actually interesting, because it gets away in getting where we want to be. So it's something, and AI can, with the numerous experiments done on lithium by many groups, for example, AI can solve that problem. What happens exactly right there? Because we happen to ignore those little like things. And yeah. So, and I see a couple of new drugs. Yeah, that's exactly. The pharmas, they are for drug discovery, for any for anything that you want to use in knowledge that you have and look through a database to look for the new compounds that has those, based on you have the knowledge, you have the infrastructure, the AI is going to be your greatest friend. It can predict for you. If it doesn't work, then you know that there is something wrong with the model. Either you can train your AI, or you can just go back and see if there is any new physics that you haven't thought about. Yeah, and we are gonna, I think that our theory collaborators, they are using a lot. In medical science, I think AI is something that people been using when they're doing like the imaging, brain imaging, like any kind of imaging, they always use AI assisted things. They don't sit down and go pixel by pixel to find something. They've been using it. So they are not threatened by the AI. We should change our view in material science as well, because that can help us discover new things and move forward. rather than sitting and insisting on doing something that the computer does faster for us. And I think we are looking for an era that is unimaginable for us the next 20 years or so. More than many people are scared of losing jobs. Many people are scared of AI replacing them. I'm more excited about the new possibilities that AI help us to not do some of those works that are now like can be grunt work. I mean, why do we want to do the work that is can be done much faster? We used to think about it. We used to people generations before us, they were taking classes for calculation for doing. Most of us don't do that anymore. We just use our calculator. But when they were sending the man to the moon, the human calculator, that was one of the scientific work that they were doing to calculate the orbits and the paths that to get the spaceships in the proper orbit. Those massive calculations, they can be done now they can be done very well by the with calculators and computers. Why not AI? AI is gonna help us to do the things that are not really necessarily productive, do it more productive. I mean, it's just become more productive, and we can explore. Unless you think the knowledge, there's a limit to the knowledge, I think AI is going to be more helpful than threatening. Because I think if it makes us move faster, we are going to reach out to explore bigger horizons, understand more. The universe, astrophysics is going to, wow, that's going to be amazing in the next 20 years, how much we learn. And with all those James Webb Telescope and all the data that is coming, I think there is so much that we are going to learn about the universe.
Well, are there any other questions? I know it's almost 8:30 in Utah.
Yeah, it is. Yeah, neuroscience too. Yes, we don't understand very much about our brain and how it works. We are going to learn so much. It's just exciting time that we can that's gonna basically help us to explore, to learn a lot more about the world. We are stuck with the complexity of how much data we have. We started getting really high quality data in science within the past 2 or 3 decades. And then the volume of data and our ability to analyze these became a burden. Now here is AI. And we can make sense of all this data that is sitting there and connect the dots. And it's great. We're going to learn more. And I think our human mind also finds new ways that we can't imagine to be creative and to think. Okay. Thank you so much for being around. This was wonderful to, yeah, we have to ask AI the right questions. Yes. And we have to give it right, right input. Thank you so much, everyone.
Yeah, thank you for the amazing talk. I know it's kind of late in Utah. Yeah, and your question, maybe we can follow up with you in
Please
email.
send me any questions you have, and yes, yeah, I would be glad to answer them.
Thank you all for the participation, and have a good evening.
Thank you so much. Good evening.